Hi, my name is Akilah Tate, and this is my Lab 3 presentation on the black hole. So for the introduction of this lab, the purpose was to find the mass of a black hole based on the information about a star's motion, and also to find the initial velocity of a spaceship in order to avoid the black hole. Two fundamental physics principles that I use for this lab are Newton's second law, which includes the formula for net force, velocity update, and position update, as well as the formula for universal gravitational force. So the main result of this lab was that the mass of the black hole was 1.22 times 10 to the 40th kilograms, and the initial velocity of my spaceship was the vector negative 4.52 times 10 to the ninth, 4.52 times 10 to the ninth, 0. So for the system and surroundings of part 1, the system is the black hole and the surroundings are the star, and the initial conditions are that the mass of the star is 2 times 10 to the 30th kilograms, and the time for my first observation point was 0 seconds. So here we have my code, which I found the initial and final momentum vectors and the star's change in velocity and momentum, net force, and its components to find the mass of the black hole. When calculating the perpendicular net force, it's important to note that the net force is equal to the sum of its components, so the perpendicular net force is equal to the net force minus its parallel component. The arrows in my code represent the net force and its components. So for the results of part 1, I have that my net force is 7.35 times 10 to the 38th. My net force parallel is 3.13 times 10 to the 37th, and my net force perpendicular is 7.3 times 10 to the 38th. And to calculate the mass of my black hole, I use this formula here, which is similar to our universal gravitational force formula. I just switched the variables around to be able to solve for the mass. And then I found that the mass of the black hole was 1.22 times 10 to the 40th kilograms. So for part 2, I had to find the initial velocity of the spaceship, and the system in this case was the spaceship, and the surroundings were the black hole and the planet, and my initial conditions were that the mass of the black hole was 1.22 times 10 to the 40th kilograms. So for my code for part 2, I found the distance vectors needed for the universal gravitational force formula, and I used them in the equation for the universal gravitational force. Then I found the net forces and used the velocity and position update formulas to find the spaceship's position. So my results for part 2 show that the ship gets close to the black hole, but it doesn't interfere with it. The ship's trajectory is altered by the black hole's gravity. The ship is able to escape the system, and the ship doesn't crash into the black hole or the planet. The initial velocity was negative 4.52 times 10 to the ninth, 4.52 times 10 to the ninth, 0. Possible sources of error are the time step size, or delta t. Larger steps can miss details, while smaller steps increase the computation time. And my initial conditions could have had errors such as incorrect velocities. There could have been mistakes in setting initial speeds, which could alter the trajectory, as well as positioning. There could be incorrect initial positions of objects, which could lead to unrealistic results. So for the discussion, what does it mean? Well, we see that net force is equal to dp over dt, and perpendicular and parallel components of each are mathematically the same. The direction of net force perpendicular and net force parallel is easy to observe, however, its magnitude is harder to measure. The rate of momentum is generally easy to observe and measure because you only need an object's mass, velocity, and time interval to calculate. What if? There will be lower velocity in the x component and similar velocity to the original in the y component. So in conclusion, I calculated the mass of the black hole and found initial velocity of the spaceship required to avoid crashing. I used Newton's second law and the universal gravitational force for my calculations, and I observed similarities and differences between the change in momentum and the net force. Thank you.